mentioned what equilibrium is before, but we haven't really talked that much about it. So far we've assumed that our reactions go to completion, meaning they run until one of the reactants runs out. So not all reactions go to completion. One example is when we have limiting reactant reactions, which means that we have an excess amount, or an amount of the excess reactant left over with the products, and we can do calculations with that, but we know that we have something left over. Another reaction would be when the system reaches chemical equilibrium. Chemical equilibrium is a state where the concentrations of all reactants and products remain constant with time. So they are actually in a very dynamic state. So any chemical reactions carried out in a closed vessel will reach this equilibrium. Sometimes they favor the products. And when they favor the products, that means that it will appear to us that the reaction is found in completion. So when it's saying that the products are favored, we say that the equilibrium position lies far to the right, meaning it's pointing or it's in the direction of the products. If it favors the reactants, this means that to us, we will probably not be able to see that a reaction has taken place. It's virtually undetectable to us, and the equilibrium position lies far to the left, so in the direction of the reactants. Okay, so our equilibrium condition. No changes occur in the concentrations of reactants or products in a reaction system at equilibrium. It may appear that everything is stopped, but it doesn't actually happen like that. On the molecular level, equilibrium is a highly dynamic situation, meaning there's lots of frantic activity happening. There is a forward reaction and a reverse reaction. So for our example, we are going to consider the reaction between water, vapor, and carbon monoxide gas. And that funky arrow is the equilibrium arrow to form hydrogen gas and carbon dioxide gas. Okay, so the forward reaction would be reactants turning into products. So H2O plus CO makes H2 plus CO2. The reverse reaction is the products turning back into reactants. So H2 and CO2 react back together to make water and our carbon monoxide. Okay, so this picture is on the next page of your note packet. It's also found on page 609 in your book. So we have H2O molecules and our CO molecules all in a closed vessel. Okay, and then after some time, they start forming the products. So now we have our H2 and our CO2. Okay, so when we have our products starting to form, things are changing inside of the vessel. But at some point, equilibrium is reached. So picture C shows equilibrium, where it's pretty constant. And so from then on, once it reaches equilibrium, the numbers do not change. So if you notice in boxes 3, or C and D, there's 1, 2, 3, 4, 5 H2s in both of them. Okay, so the number of molecules no longer changes. But the reaction isn't done. It's constantly going in the forward and the reverse reactions, moving back and forth. Okay, so sometimes we'll have the reactants go together to make the products, and then sometimes the products will go back towards the reactants. It's this dynamic, frantic activity going on. These two graphs show, on the top one is the concentration of the reactants and products over time. So if you notice, the red line is the products, and that starts at 0, concentration at time 0, because we are assuming that we only have reactants to start. So reactants are up high. And so then, as the time goes through for the reaction to take place, the concentration of the reactants lowers, and the concentration of the products increases because the reactants make the products, but then after some time, the concentrations become equal, where they become linear and they even out. And when they even out like that, that's when we reach our equilibrium from there on out. Okay? But the reaction rates, which is the bottom graph, shows that the reaction rates don't happen at the same proportion, or they don't always change in the same way. Because, like for this example, the forward reaction, where we have our reactants turning into products, is more favored than the reverse reaction. And so the drop in the forward rate is bigger than the increase in the reverse rate. But at some time, the rates even out, they're equal to each other, and so that's when equilibrium happens. They're even, they're constantly happening. Okay, so this is the end of level 57. There's no quiz for this level. It's combined with level 58, but you do have 2 homework problems, number 10 and number 11.
Wish I had me a time machine. Oh, I